Hello and welcome to Everyday Science, where I try to help you appreciate the scientific wonders of our daily lives. So here's a C on a guitar. But here's the same note on the keyboard. Now, despite being the same pitch, both the guitar and piano clearly sounded different. But why is this? Well, first, let's pretend the piano was a grand piano, the keyboard was a grand piano. Because first of all, it's good for explanation since both contain strings, the grand piano and the guitar. Second of all, I don't have enough money or room to fit a grand piano in here. So let's look at how the sound is produced. So I think we all know that the strings vibrate in the guitar and piano, causing the air molecules in the air to vibrate, which we hear. Now, if both instruments only played the note C, which I was playing, then you would hear a sine wave which looks and sounds like this. So clearly we did not get a sine wave when we played the guitar or the piano. And even look at the frequency spectrum for a guitar, it looks nothing like the sine wave that we got before. So what is actually happening is that everything, all guitars, all pianos, all sounds that aren't sound waves are actually made up of a combination of different frequencies of sine waves, which you can see in the image of the frequency spectrum for the guitar. So now what's happening with the piano and the guitar, why they sound different, is because the piano has a different combination of frequencies to a guitar. So let's look at this in a bit more detail. So what happens when you play the guitar string like this is you create two transverse waves moving outwards from where you plugged it. What I mean by transverse, it makes the string wobble up and down while the wave's moving that way and that way. So basically it's a sine wave. It makes the string wobble up and down while moving perpendicular to the wibble wobbling of the string. And now what these two waves do, what the air goes to either side and they're stopped by the guitar, and because they can't move any further because the string is suspended in these two places. And so what happens, since the energy and the wave has nowhere to go, it bounces back throughout the string. And of course these two meet because they're heading towards each other, and they travel right through and they keep bouncing backwards and forwards, and you get an interference pattern. So the waves meeting at all points on the string. We call this a standing wave because, well, it's two waves making another wave bouncing backwards and forwards. And now what happens is what we call superposition, and I'll explain this. It's if you take a wave that's moving up and down in the string and you compare it to where the string would be when it's normal, when it's straight like this and not being played, it would have a distance above or below the string, and you call the distance below a negative number and the distance above a positive number. So then where these two waves meet, you would add this distance together. So if it's a negative and a positive, you take the negative away from the positive because the two strings are in the same place, so the two waves are in the same place, and the vibrations sort of cancel each other out or add onto each other. And so where you have a maximum and a minimum on one string and the other one, or a peak and a trough, and there are equal positive and negative values, they will completely cancel out and you get something called a node. This is a point of the standing wave where the wave doesn't move, which is quite strange because you'd expect a wave to move, but it's because of the two different waves being at opposite cycles of phase, or being out of phase, basically one's at a trough and one's at a peak, and that means that it cancels out there and we call that a node. And now where they add together, so where one's at a peak and another's at a peak, or were either of them at the maximum at the same point, they will both make a peak or a antinode in the standing wave. Or where they both are meeting in the negative way, they also make a antinode, but this would be a trough in the standing wave. So as I said before, the guitar actually makes several different frequencies when you play it. So you don't get this just one standing wave, you also get these other frequencies going out to either side and coming back and making an interference pattern and other standing waves of different frequencies. So you have all these bunch of nodes and antinodes throughout the whole string, which you might not think when you first look at it, because a string doesn't have any points where it doesn't move apart from the ends, of course, which you would expect it not to move at. But throughout the whole string it just looks like a one sort of wavelength, it doesn't look like anything special. But this is actually false. It's not one wave. It's a bunch of different standing waves all added together to make this one pattern. And now you can actually get around this by doing pitch harmonics. So I'll demonstrate what they are right now. So a pitch harmonic is when you touch a string and you get a high-pitched sound like this. In contrast to when you play it down fully, you get a sound like this. And in contrast to when you play it open like this. So to understand this, we need to understand that when you plug this guitar in originally, you don't just send one wave to one side and one wave to the other side, you send a spectrum of waves to either side So you get a spectrum of different frequencies going one side, and you get the same to the other side, one for each frequency. Now these bounce back and create an interference pattern of their own, so each one has their own standing wave. And now you'll see a picture on the screen now which is showing all the different standing waves in a string. Now the lower frequencies have long wavelengths, so you see the longest wavelength, which is the lowest frequency, goes right from one end to right to the other, because that is the lowest possible one you can get, because you need nodes either side where it's not moving. So this is the lowest frequency one, and therefore this is why you don't actually see any nodes throughout, because this one sort of overpowers the rest of each of the others. The others add up to make somewhat of a similar pattern, and it just smooths it out and you don't get any points where it's not moving. And then the higher frequency ones have more nodes because they've got more peaks and more troughs meeting each other, and so they cancel each other out in more places, which is kind of confusing. You need to get your head around it. But what happens is when you touch a point where it's moving, or an antinode, or just any point on the string where it's moving, you will get the string stopping. The wave stops because the energy is transferred into your finger or whatever you touch it with. And now if you touch a node, since the string's not actually moving there, you don't do anything to the sound. So the clever thing is touching the string, or touching the strings, or the certain actual standing waves where they're moving, while touching the other standing waves where the nodes are. So if you touch where the nodes are, if you can see on the picture on the screen now, so touch one of the nodes on the higher frequencies, you'll actually be touching a place on the lower frequencies where it's moving. So you'll actually stop the lower frequencies because the energy will be transferred into your finger, and there you will leave the higher frequencies still vibrating. So then you'll have the higher frequencies vibrating, but then the lower strings cancel out, or the lower frequencies cancel out in the open string which you've just played. So basically the open string is made up of all of these notes, of all of these frequencies, and then you can pick ones out by touching points where they're moving, and then keep the other ones remained in where they're not moving by touching that point. And what interesting thing is where you touch the middle of the string on the 12th fret, you actually take out only the longest wavelength, going from side to side, and you actually get the same sound as when you press down fully on the 12th fret, which would create all the frequencies but halved, if that makes sense, and therefore you get the same frequency when you do a pitch harmonic on the 12th fret as when you press it down fully. To demonstrate what I just mentioned, by touching the 12th fret and then also playing it, it should give you the same sound. So pitch harmonic on the 12th fret and then pressing it down, it's the same pitch, and that is because when you touch the 12th fret you're actually getting the frequencies from here to here, which is half the distance from here to here, so you would expect half the wavelength, so twice the frequency. But then when you also do the open string and cut out the full wavelength, you actually get a node here, and you get all the standing waves from this point to this point and this point to this point, which is half the frequency of the full string, if you understand what I'm trying to say. And so actually you can actually see points on the string where it's not moving, and now you have to do this yourself if you want to do some good pitch harmonics, because I can't really show it with this camera, but you can literally see points where it doesn't move and points where it does move. But what I can demonstrate is that when I do this and I touch down at this point on the node, nothing happens to the sound because, well, there's no movement there, so no energy is being transferred. But when I do that and then touch here, the sound is cancelled out. So you can clearly see that there are nodes. And the cool thing is, when you do a node like here, you will have several different nodes throughout the string, so you can touch different points on the string and you'll be able to find where every individual node is by touching, and if the sound stays, you'll have found another node. But what you might be thinking is that at the start I said that there was one pitch. I played a C on the guitar and the piano, and obviously that was a C, that was the one C pitch. But then throughout the whole video I've been saying, no, this isn't a C, this is a bunch of different frequencies, all different, these different notes. But clearly when you play a guitar or a piano, you get C. You don't get these bunch of different frequencies from that one instrument. You can clearly hear it's C. And the reason for this is because our brains interpret this distribution of these combination of frequencies as one pitch. And why this is because if we heard everything in different pitches and we heard the individual pitches that make up absolutely everything, we wouldn't be able to distinguish everything. We'd just hear all these frequencies and they'd be baffling our minds. So what evolution has caused us to do is interpret each sound as and combining all the different frequencies of that sound into one pitch, but then giving it a texture based on all the different frequencies, which is very useful in evolution because then you can distinguish between sounds of different things, and you can hear when something's a hawk and coming to kill you, or when something is the rustling in a bush and you got to be cautious, or anything like that, or the rush of the wind. You can distinguish between absolutely everything that produces a different spectrum of frequencies. Now the cool thing is what scientists do, music technology scientists and just general music physics scientists, can actually get a waveform of music, like I showed you before with the guitar. You can actually see the sine waves all added together, and they can separate that sound or the frequency spectrum into the individual sine waves that make it up, so you can work out what frequencies make up that individual sound. And you can identify specific objects with the specific frequencies using technology, which is quite interesting. So I said the human brain interprets all sound as a single frequency before, with instruments a single frequency. But what you may be thinking is, what about a car driving past on tarmac, or just any sound that you can't pinpoint a frequency to, mainly non-musical instruments? And your brain does interpret this as one particular sound, but why is it not a particular frequency? So to look at this, we've got to think of a guitar again. So a guitar, either side, you have 2 points that stop the string from moving. So at this point, these 2 points, you're forced to have a note at these points. All other waves are cancelled out because it stops the strings at these points, and that's why you get these particular waves that are standing waves that are on the string, because all of those stop at this point and all of the ones are cancelled out because they're stopped by either side. And now this makes all the waves produced in a string factors of that the longest wavelength, because they've all got to reach this point, so they've all got to be factors and multiples of each other, and that is what your brain interprets as a good pitch. That's something that you can relate into one pitch, because they're all similar. They all have these factors between them, and your brain likes factors. Your brain like even multiples of each other. And now things with like car driving and tarmac, there's no limits. There's lots of limits. I don't know how you want to think of it, but there's no limits to where the sound can go. It can go everywhere, and then it can be stopped by anywhere, and you don't get any particular frequencies. There's no factors of frequencies. There's just bizarre frequencies that got cancel out, and you get this multitude of stupidly non-conforming frequencies that your brain can't interpret as a single frequency, because it would make sense to pick a single frequency out of it, because there's so many different ones that don't conform, and therefore you get a sound that isn't a certain pitch. So to conclude, all sounds in the world everywhere are all made up of different frequencies and a spectrum of different frequencies, and musical instruments have this conformed multiple and factors and of each other, and they're all conformed into this one little space because they've got nodes at either side, even things like flutes and all instruments. And this is because they have something called longitudinal waves, which are basically waves that go like that, and not transverse waves that go like that. Basically air molecules bouncing into each other and passing a wave downwards. But I'm not going to get into that because it's a little bit more complicated and a little bit more difficult to understand. But it's the same principle with all instruments. And sounds that don't have a particular pitch are just random everywhere waves that your brain can't comprehend, because your brain likes factors and multiples. So of course, this is my first video here on Strange and Quarky, my new channel. Hopefully you enjoyed it. I'll be doing lots of physics and science videos. If you have any suggestions, feel free to comment down below. Any questions, comment down below. I really hope you understood this. Hopefully I'll get better. Anyway, thank you for watching, and I'll see you next time.